Hi, I'm Zor. Welcome to Unizor Education. We continue talking about planetary movements. In this particular case, I would like to talk about characteristics of the motion, planetary motion, in polar coordinates. Now, why polar coordinates? Well, in one of the lectures, which was before, about the first Kepler's law, we saw that polar coordinates play a very important role in derivation of the first Kepler's law. It's just easier to do it this way, and we can come up with certain results much faster. Now, what I'm talking today is just yet another approach, a little bit more, I would say, pure polar coordinate approach. So I will derive certain differential equation of planetary movement using a little bit more polar coordinates than before. Again, it's all about how to get easier to final solution. Now, this lecture is part of the course called Physics Plus for all. So if you want to go to this lecture on the unizor.com website, you have to go to this course, Physics Plus for All, and choose Laws of Newton chapter or part, whatever, and the lecture is called Motion in Polar Coordinates. Again, this is something which we have already addressed in the previous lecture about first Kepler's law. It's just yet a little bit more information about polar coordinates and motion in polar coordinates, because it's very important for all these cosmological problems. Okay. Now, what we are talking about. First of all, very quick reminder, what is polar coordinates on the plane? We are talking about a two-dimensional case. Well, basically, you have to have certain origin of coordinates. You have to have certain axis, which we will call the basis axis or whatever. Now, it's fixed on the plane. Now, then every coordinate is determined by an angle from the base axis. Usually it's used theta, and the radial distance from the origin of coordinates. So these two parameters, r and theta, uniquely identify the point on the plane. Okay, fine. So in these coordinates, r and theta, we will try to establish parameters of the motion. And most important parameters are position, velocity, and acceleration. These are all three vectors, and all these three vectors we would like to express in these in this terminology, in radial distance and angle of rotation from the basis. Okay, great. Now, so let's talk about plane first of all. Which plane are we talking about? Not every plane. Now, when we are talking about movement in the central gravitational field, we have already established many times that this motion is flat. So the trajectory always in the same plane, and the source of gravitation, the central gravitational field, is on that particular plane. The reason for this is very simple. We were proving this before, but from the physical standpoint, central force does not have any kind of a torque. It does not rotate. It only gravitates towards the center. So that's why there is no extra rotation, which means whenever some object, test object, goes into the gravitational field, all gravitational field is just acting within this one particular plane where the whole trajectory is located, and the center of the gravitation is in that plane. So we have established the plane. Now, next we have to establish the origin of coordinates. well, yeah, obvious choice. If you have a plane where some test objects are moving and there is a central gravitational force, that center is most conveniently to take as an origin of coordinates. So if we are talking about planets and sun, then we are talking about coordinate system with origin at sun, and the plane is the plane where the planet is moving. By the way, all the planets around the sun are moving approximately in the same plane approximately. But in any case, if we are talking about one particular object, one particular planet, then yes, this is basically the plane where it moves, and that's the plane we're talking about. Now, the next question is, so we have the plane, let's say this board is the plane of movement, so the planets are moving somewhere here, sun is here, so we have a center, so we need the base axis from which we will start basically counting the angle of rotation. Well, there is no such thing. The only thing we can do is, at certain particular moment of time, the fixed position of the planet and the direction, so this is a t is equal to 0, whatever the t equal to 0 is, we just choose it, basically, and that would be the direction of the base axis. And then the planet moves somehow, and we will start counting this angle from this base position. So this is at some time t. Okay. So we have established basically our coordinate system. Now, let's assume that we have the central source of gravitation with mass m, and our test object, our planet or whatever, has lowercase m as the mass. Now, on this plane, coordinates of this point always 0, 0, because it's the origin of coordinates. So the radius is equal to 0, and the angle is equal to 0. Coordinates of test object would be some kind of r and theta. Both r is function of time, obviously, and theta is function of time. So they are changing. So as a planet movement at time t, our planet would be in this particular position, and it's all time dependent. Now, at the same time, we can introduce Cartesian coordinates, and that would be actually very conveniently, because we will switch from one coordinate system to another to establish certain equation between the radius and angle theta. So obviously the coordinate system, Cartesian system in this particular case would be, if we will assign this is OX axis, and this would be our OY axis, with O origin of coordinate will be at the point where the source of gravitation is. So we have now two systems. We have XY system, and again X is fixed where the base axis for radial for polar coordinates is, and also we have a radial system, polar system of coordinate where radial and theta angle are important. Okay. Now, if, for example, our coordinates in Cartesian coordinates of this object are x and y, it means that let's introduce unit vectors along x and y coordinates. Usually it's I and j. So unit vectors, they have unit lengths and the direction along the x or y. So in this case, our vector let's call this point P. So P would be coordinates x, y, but at the same time we can have that the vector, let's put it this way, vector OP can be expressed as x times y plus y times j. So if x is coordinate along the x-axis and y coordinate of the point P, x and y, then using unit vectors, we can express vector OP, which is vector of position, and we sometimes use the r. Now this r and this r are different. This is the vector and this is the length of this vector, okay? So we can express it this way. At the same time, I can express it differently. What is x? What is x coordinate? If I have the radius and the angle, then x is r cosine theta I plus r sine theta j. So this is just a different representation of the same thing, because x is obviously r times cosine of this angle and y is the sine. Now obviously r and theta are function of time, as well as x and y are function of time as our movement, our test object is moving. Okay, now, so we have introduced this kind of Cartesian system for the motion of this, but it's not very convenient for converging into radius and angle. To basically have this type of representation very convenient in polar coordinate, we will introduce another pseudo-Cartesian, I would say, system of coordinates. System of coordinates which is actually turning with the position of this our test object. So we will have one axis in this direction and one axis in perpendicular to this direction. And this also we will have some kind of a unit vector, which I will put like ER with a circumflex, and unit vector here would be excuse me, would be E theta. So these are two unit vectors. This unit vector is always along the direction where the test object is located, and it's turning with, as object is moving. This coordinate system defined by unit vectors ER and E theta are also moving. That's why I call them like a pseudo-Cartesian system. But I mean, it's Cartesian because it's perpendicular, but it's moving always with our test object. As it moves in the plane of motion, this pseudo-Cartesian system is turning with it. So it's, the ER is a moving vector, it's function of time, okay, and it's always directed towards the object. Now, in this particular system of coordinates, our vector r, which is OP, the same thing, can be expressed a little bit simpler. It's length times the unit vector. So, in moving pseudo-Cartesian system of coordinates with ER and E theta towards our coordinates, it's much simpler representation. So this is one of the keys why the whole thing is basically introduced. So it looks like to do it in this particular system is simpler. As you see, it's much simpler than this. Okay. Now, since our system of coordinates is moving, it's not fixed, basically. And that actually gives some complications which we will be able to circumvent. Now, in case of Cartesian system of coordinates, we can have a very simple representation of velocity and acceleration. Since I and j vectors are constant vectors, this is a system which is not moving. If I would like to differentiate this to find the vector of velocity, well, that's basically the derivative of vector of position. And in plane Cartesian system, since I and j are constant, it's just derivative of x times y. So the apostrophe is just a differentiation by time, dx by dt if you wish, but these are the only to be differentiated because they are because I and j are constant. Now, if I will have this representation, that would be much more complex, because yes, I and j are still constant, but this is supposed to be differentiated how? I mean, it's r derivative times cosine plus r multiplied by cosine derivative, which is minus sine times derivative of inner function, which is theta. So that would be kind of complicated thing. But in this particular system of coordinates, which is moving with, it's simpler. Not as simple as in Cartesian, but still simpler, and the final result would be simple enough. Okay, so how can we differentiate this? Well, to find again velocity, we have to differentiate this, but r is changing with the time and er is changing with the time. So basically it's r times er plus r times er. So either we differentiate this or we differentiate this. Remember, if you have uv, derivative is u times v derivative plus u derivative times v. So I'm using this formula of differentiation of the product. Okay, I know what this is, but what is this? This is a much more kind of strange thing. What is the derivative of this vector, which is a unit vector going along there? Well, to find out this, we will resort back to our original Cartesian system of coordinates. And let's express vector er in ij system of coordinates. Well, if the unit is, if this is the unit length, so this is 1, so the projection onto the x-axis would be correspondingly 1 times cosine of theta times I plus sine times theta times j, projection onto this. Okay, now let's differentiate this. Okay, so er differentiation, the derivative of this is equal to derivative of cosine. I and j are constant, right? So derivative of cosine would be minus sine theta times derivative of theta itself. That would be I plus derivative of sine is a cosine theta times j. Interesting. How about e theta? This thing. Well, this thing is different from er just by 90-degree angle. It just turned around. So it's a cosine of theta plus pi over 2i and sine of, it's just a different angle, right? J equals. Now, what's a cosine of theta plus pi over 2? Well, if you remember trigonometry, it's minus sine theta. And what is sine of theta plus pi over 2? That's a cosine theta. Now, consider this and this. They are practically the same, except theta, derivative of theta as a multiplier, which means that ER derivative is equal to theta derivative times E theta. So multiplying this derivative, if you have to calculate this derivative, you just have to take this unit vector, the E theta, and multiply it by theta, the theta derivative. Similarly, if we will take the derivative of E theta, that's the derivative of this, would be what? Minus cosine times theta derivative and minus sine theta derivative, which is basically the same thing as this, except the multiplier. So it would be minus theta times ER. So derivative of ER is expressed in terms of E theta, and derivative of E theta is expressed in terms of ER. So why is it needed? It's needed for this differentiation. You see, we need differentiation of ER in this particular case. So we will use, for this, we will use this expression. And as a result, what do we have? Now we don't need this anymore. We have this is equal to derivative of R times ER plus R times derivative of this is theta E theta. So again, we have actually represented this vector as sum of two different variables. These are these are not vectors, these are vectors, ER and E theta vectors, and these are some kind of a one-dimensional variables, scalars, and so it's representation, this is representation in Cartesian system, and this is representation of the, sorry, why did I put this? Of velocity in our pseudo-Cartesian system. It's a little bit more complex, but again, we need it for further calculations, and it will be simpler further on. Just take my word for it. Okay. So we don't need this anymore. We have represented velocity. Now our next goal is to represent the acceleration. Okay, so what acceleration is a derivative of velocity, or second derivative of position. So it's R vector second derivative, which is velocity first derivative, which is the derivative of this thing. Okay? Alright, so let's differentiate it and see what happens. It's R second derivative ER plus R first derivative ER derivative. Now ER derivative, we know it's theta derivative and E theta. Hope I'm right. Second plus, okay, fine. Plus derivative of this. Now this is the product of three different variables. Each one of them is dependent on time, so we have to do it 3 times, which means what? It's derivative of the first times without change plus derivative of the second, which is second derivative of theta, and without change, plus derivative of the third one, which is this times derivative of this, and that would be minus derivative of E theta is minus theta derivative times ER. So it's R theta derivative square, because this is one and this is from this another, and would be ER, okay, minus, because E theta derivative is equal to minus theta derivative and ER. So that's the final expression. Okay, let's put together ER and E theta. So what's with ER? This is ER and this is ER. So we have R second derivative minus R theta derivative square, and it's all about vector ER. So what about vector E theta? It's R theta, R derivative, theta derivative, and another R derivative. So it's 2 R derivative, theta derivative, and this one, plus R theta E theta. And here, so this is what? This is A. This is acceleration. But now, what's interesting about acceleration is directed always along the force, because it's the second law of Newton. Remember? F is equal to m times A, and this is a vector, and this is a vector. So A and F are collinear. Now, the direction from our object towards the center of gravity, which is basically the direction of F, force F, and direction of ER basically are the same. I mean, they are collinear. I mean, ER goes this way, forces goes this way, but they are collinear, which means if we will represent the acceleration as a sum of two vectors, one goes this direction and another goes this direction should be 0. Since A and ER are parallel to each other, vector A is parallel to vector ER. Well, I usually use circumflex here, unit vector. This must be equal to 0. There is no component which is perpendicular to ER. Okay? That's from the general consideration. At the same time, we can do it in a formula, basically. I mean, we can really derive that this thing is equal to 0 analytically, and it's very simple. Now, every lecture which I put on unizor.com has video presentation and textual part. And in the textual part, on the same screen, you can see it, I do have another kind of derivation that this is equal to 0. And I don't want to waste time right now during the lecture. It's really like straightforward calculations based on this formula. This is the vector product, cross product, between position vector and velocity. This is angular momentum. And again, in central field, angular momentum is constant because there is no torque. Angular momentum can change only if there is some kind of a torque, the rotating force. This force is never rotating. This force is central. So from the constant value of this, we can derive very simply that this formula, that this is equal to 0, is true. So I put it there, and you can always take a look at this, or you can try to do it yourself by differentiating this thing. Okay, so we have come up with the formula which is actually only this. that A is equal to R minus R times square ER. Now, incidentally, again, using this thing, I have derived in the same textual part another very important formula that L over M is equal to R square. Now, in this case, I'm talking about the lengths of this vector L. These are vectors, so L is also a vector. So let's not forget this is L vector. And it's directed perpendicularly to R and V, which means it's directed perpendicularly to the plane of motion. But its length of this vector is this. And again, this is very simply proven in the textual part of my lecture. If you will have some time, maybe I will do it right now on the board, but basically that's not important. From which follows that I can substitute this to this, and what happens? A would be equal to, well, let's just drop the vector form. Let's put absolute value, basically. The length of the vector A. That's this expression, because the length of this is 1. So it will be R minus R times square of this. Square of this is L divided by M R square square is equal to, well, let's do it this way. I will put it L square M square, and R should be equal to the power of 4, but we have R here, so it will be the power of 3. So this is equation. Now, at the same time, using the Newton's universal law of gravity, you know that mass times acceleration is the force. The force is G M divided by R square. So just acceleration itself without mass would be this. And look at this. Let me just put it again. R minus L square M square R cubed is equal to GM R square. Well, except one little nuance, it should be minus, because acceleration is directed opposite to the position of the R vector. So if this is ER goes this way, this goes to this way. So that's why I have to put minus here. All right. Now this is minus here. So this is differential equation for R. Now, why is it better than Cartesian system, which we used in the very beginning? Well, in Cartesian system, you had A is equal to, well, vector A, without any kind of, it's equal to xi plus y j. You have two different variables. So it's a system of differential equations. Now here you have one differential equation with one variable r only, and that's kind of much easier, obviously, to solve. Now, to solve this is not part of this particular lecture. We will do it some other time. My purpose was to derive differential equation for a single variable, which in theory can be solved, and you can get the dependency between the radius, the distance from the source of the gravitational force, and the test object, and using the dependency between L over m is equal to r squared theta. Now from this we can always, now this is the constant, and if r we know, so we know the theta as a function of time. Well, the first derivative of theta, then we can integrate it again, and we can get the theta dependence. And as a result, we will get theta and r depending on time in some kind of reasonable formulas or whatever, which are quite complicated, but doable. Everything is doable. So again, my purpose was to derive the dependency between acceleration and the distance to source of gravitation, and combining with Newton's laws, we can get this differential equation which this distance r should satisfy. That's it. So the only thing is I did not really explicitly proving this particular formula, this is equal to 0. This is in notes for this lecture, so you go to unizor.com, physics plus, you go to laws of Newton, and the lecture is called Motion in Polar Coordinates. You will see it. It's really very simple, just a few lines of calculations which I just don't want to waste any time right now. It's all straightforward. This one and this one, they are all very, very simply derived over there. Okay, that's it for today. Again, read the notes for this lecture. It's very important because it kind of puts your mind in the right place. Also, don't forget that Unizor.com contains many other courses: Math, Math Plus, Physics for Teens, all totally free, no advertisement, nothing would distract you from learning. Knowledge is power. So just try to spend some time and enrich yourself with the knowledge. Thank you very much, and good luck.